So thank you everyone coming attending the GAP seminar this month. And welcome everybody. And let me briefly introduce Minki, who is the one of the greatest researcher from Korea, now become an assistant professor at KAIST. He was my colleague when I was doing postdoc at KIAS, and yeah, from then I saw he achieved so many great achievements, and now he will give a talk on something that I never have understood before. It's about lifting theorems from classical to quantum security. And the Professor Minki Han will give this lecture.
Okay, thank you for introduction. Uh, I don't think it is a lecture, but feel free to ask anything in the middle of the presentation. And I think most of the technical parts are done by my co-author, and I barely understood it, so I studied it to present this. So let's study together. But I think some of the proof are very slick, so I'm not sure I can explain that kind of detail in English, but let me try. Okay, in this talk, I will talk about the lifting theorem. This is a kind of a magic theorem that reduces the quantum security of some primitive to the just classical security without invoking anything. So if you use that kind of thing, you don't need to know anything about quantum, so it's good. But there are many drawbacks, so but I will explain probably at the end of the talk. And in this talk, I try to explain the proof, and the proof is of course quantum, but I try to avoid quantum in many cases or whatever. But I'm not sure. I think I need to assume that you know something about quantum, like bracket notation or measurement, probably that kind of thing, or some norms or something. And at least half of the talk is about the classical lifting theorem. We actually have a classical lifting theorem. We probably never use it to prove some classical result, but anyway, we have one. And I want to acknowledge that many parts of this talk is actually Shippen taught me about it. So thanks, Shippen. So uh, today I talk about this kind of thing. The first thing is quantum gossips, because I think some of you are curious about some quantum or some recent news about quantum. So I include it just for fun. And then I explain the classical lifting theorem in detail with the proof. And I show how to extend it to quantum setting. It requires some quantum knowledge, but I try to explain everything from scratch without invoking any technical theoretical research or something. And finally, I'm going to the permutation lifting, which is my paper. But I think this part has 3 or 4 slides, so whatever. And then I'll explain some open problems or open direction that derive from these lifting theorems. So let's start from gossips. We know the Shor's algorithm is likely to break RSA or HTTP or something like that. And I think many people set the timeline or Q date to the 2035. But last week we have 2 more papers. They are about the optimizing the implementation of Shor's algorithm. So one paper said that if we just make 10,000 physical qubit, we can break the factoring technically. Or another thing is some improvement of the Shor's algorithm for ECDRP. Just for fun, let's see some detail. In this paper, they have this kind of graph. They estimate the number of physical qubit and the time to break RSA and ECC. But here, their title is 10,000 and their time is more than one. 100 years, so it's just for title. But anyway, actually it's better than the we know what we know before. Yeah, I think it's more important. It's quite quick and it's quite small. I think previously we only know something about the 100,000 qubit to break ECC and RSA, but it's much faster and using a smaller number of qubits. In the another paper, the authors used the zero nodes to show that they actually have a circuit, but they don't want to disclose the circuit because they think it is too severe or something like that. And they use the pre-quantum zero knowledge, so it's probably the only application of pre-quantum zero knowledge proof to the quantum world. And according to their estimation, the number of qubits and logical qubits and the topology gates are not very different from the 32-bit to the 256. So it means if we see the break of BCDLP or something in a small scale, we probably can break the large scale CDAP in a few years or something. I think one of the author of this paper mentioned that probably with 10% or something, we can see the break of RSA in 2029, just 3 year. I'm not sure it is true, but we probably need to prepare something about post-quantum. And it's just gossip, and we are moved to the symmetric key crypto. There are a bunch of topics, and probably you know many, but I just introduce some things. From the attack side, Grover usually give a quadratic speed up, and it is known that sometimes there is a better attacks, like beyond quadratic speed up for some symmetric scheme. I think they obtained a 2.5 exponent speed up, or sometimes worse because in the symmetric crypto system, we cannot, for example, we cannot access the encryption quantumly. So something are quantum and something are classical, so the model is a bit complicated. But never mind about this kind of complicated example. In this talk, I will only talk about simpler examples and proof about the proof of security. So we need to talk about the security proof. For the classical, in the symmetric system, we usually use the idealized model or random oracles to argue the security. And in the classical setting, we have a bunch of nice technique like lazy sampling or programming or whatever. We have so many things, and analyzing the bad events are usually very easy. But these kind of things are all become non-trivial in the quantum setting. So we have some methods. For example, we have an adversary polynomial method. This is the kind of the first technique to prove the quantum lower bound, but it is usually very complicated to apply in the cryptographic setting. In 2019, Mark Gentry found a kind of quantum lazy sampling, which is called the compressed oracle technique. And based on this, we now know how to analyze many random oracle stuff in the quantum setting. And we have a several programming, resampling, or one-way hiding lemmas. But actually, these kind of techniques are about the kind of changing the thing very slightly. So if we invoke the last two, we may need a bunch of hybrids or analyze every details or something like that. And for the compressed oracle, while it is very nice technique, it turns out that when you try to prove something using compressed oracle, it is usually very complicated. And I already know many papers that include some bugs or minor or major. I think Ashwin found some bug of the one of the first application of compressed oracle. So they are occasionally very hard to analyze. So the question, can we hope to have some easy quantum proof or quantum proof, friendly one-shot proof, or upgrade flashcard to quantum or whatever, at least for some problems. So ideally, we hope something like this. Whenever we have some classically secure primitive in the random oracle model or permutation or idealized model, we hope to have quantum security somehow. I think actually there are not many counterexamples of this argument. If something is classically secure, then it is quantumly secure with respect to the random oracle or ideal cipher. So probably if we add some conditions or something, maybe we can hope. And this is the lifting theorem. So I will start the lifting theorem. I think this is start from the Yamakawa Jandri Eurocrypt 2021. So I will introduce some sleek proof of idealized model problems. I think I saw this proof only in this paper. So, but anyway, so we are talking about the classical lifting theorem first. Oh no, we are talking about the a bit detail of the lifting theorem first. The ideal version of the lifting theorem is looks like this. If we have some quantum algorithm that break some security or win the security game or something, then the idealized version of the lifting theorem says that the advantage of the quantum adversary is bounded by some classical adversary. Here you can see we only have a classical rocker, and probably we need to have some factor because quantum security is usually worse than the classical security. So this is the idealized version. And we, as I said, we actually have this kind of theorem, and we have some application. We probably see a bit. For example, we can show you the random rocker one-wayness or collision resistance or security of some signature or constant long sponge collision resistance or whatever using this lifting theorem. So since quantum is too hard, we are starting from the classical. But what's the point of the classical lifting theorem? The algorithm A and the algorithm B. I mean, we hope that for any algorithm A, there is algorithm B such that this kind of thing holds. But it's a bit weird because A and B are try to break the same problem and they are classical. So maybe it looks there is no point. But the lifting theorem actually reduces the many classical query adversary to the few classical query adversary. So we can reduce the number of queries. Actually, in many cases, we only need to make a constant number of query or whatever. We will see what's going on. And if we only make a constant number of query, it's not very hard to analyze. While this kind of thing, we may need to analyze the database or input-output pairs or whatever. So we actually put this one for the one-way function. We are thinking about the simplest problem, zero preimage finding. Let's consider some flashcard adversary making T queries and eventually output the candidate solution X star. Uh, Maybe A will make a query. Otherwise, it's a random essentially. So maybe A make a query. This is the first observation. And we know that the ACE query input-output pairs are written by this. So yeah, I think you are very familiar that if we pick this kind of thing, ACE behavior is essentially the same. It just defines the advantage of A. So we are thinking about this case. What if I is the smallest query such that this query is star? Then we can see that this one, x1 to xi minus 1 are not x star. So actually, we can just change the oracle for the first I minus 1 query, where G is the another independent random oracle that is not H. From H's perspective, these two input-output sequences are just identical. And here you can see that the number of queries are reduced. And we can proceed further. We can define a reprogramming of G, where here we write, I will use this notation many times, so please remember this. This reprogramming says that G, A, comma B, say that this function is basically G, but only for the input A, it output B, then GA. And we will write the G prime as a reprogramming of G such that the output on Xi is just HXI. Then this above sequence and this below sequence look just identical to the A's perspective, right? Then here, this is A's view, and in this view, we only use the single query to H, this one. So this is the main observation of the lifting theorem. Based on this one, we can define the simulator. Here, instead of the simulator B, instead of using H, it defines its own random marker G and try to guess the actual output query. X star supposed to be the outcome of A, and we just guess where it is. Here both means that X star is never queried by A. Otherwise, I is the index that A query X star for the first time. Then B learns A, but the oracle is different. Instead of using directly H, it just do this thing. For the first I minus 1 query, it answer everything using G. And in the I's query, it make the query to the H and get HXI and give HXI to the algorithm A. Then it reprograms G prime to the XI comma HXI. Then for the remainder query, it just used G prime to answer the algorithm A's query. Then whatever A outputs, the simulator B just return the same thing. Here, adversary's algorithm A views exactly this, and we already saw that this is basically identical to the query made by H. And this guess, this is a uniform random guess, and among the t plus 1 choice. So this guess is always true with probably 1 over t plus 1. And if the guess is correct, P simulate A perfectly. So we have this. This is the main idea of the lifting theorem.
Uh, Sorry, Minki,
Yeah.
But this is under the assumption that you have only one pre-image, right? Because what if there is another xi xj where j is less than I and h of xj is also equal to 0? Then
Yes.
adversary may query
But
that, and then
oh,
the g value may be different for that, right?
yeah. Actually, for that, I assume that the algorithm may output X star. This
Ah,
assumption is important.
so this x star is some fixed value, or
Yeah, actually that's a tricky part. I think this already gives some intuition, but I think this is kind of incorrect because of the kind of not minor subtle issue. The problem is actually I just proved something, claim something like this,
hmm.
but as you see, there is a dependency between here the output and reprogramming.
Yes.
It yeah, it bugs me a lot. I'm not sure just as is it is true or not. So we actually need a little more complicated argument. Yeah, thank you. Good question. So we will resolve this issue using this. We use the same simulator, but we actually do this thing for any oracle H and any input X. Wait, yeah, forget about this. And we actually be even sample the oracle in an arbitrary manner on its own. Uh, yeah, here for any X, this random guess is just the guessing the position of the first query index of X, this X, not Xi. Then if the guessing is correct, A learns this one. And here you can see that outcome P output is always the same as A. So this is actually what we can say safely. But here we relax everything like G and H is any workers and exchange is arbitrary. So here I remove the dependency between the reprogramming and outcome. Then we have this. What we actually can prove is this, but we actually can prove this kind of thing for any XC and the any oracle GH. Then we just take the expectation over all random G and H so that this H becomes random and this becomes random. Then we just sum everything by the condition that G and X is the same and G is such that the HG is 0. Then the left hand side is this. And the right hand side is this. This is a random worker and this is the reprogrammed one. So to remove the dependency stuff, we actually do this kind of argument. And here, we only make the single query, and actually that query is C. And we assume that I make T query. So we have this. The probability that A output C such that the preimage of H is bounded by T plus 1 times the advantage of B. But here, B query something and output this. So this is basically just a random value. So this is just the I think it should be Y. Here B query Z, but it does not use any information of Z. So HZ is just a random value, and this is the result of the lifting theorem. We will use this kind of argument many times. So this is the single coil lifting theorem, and we can extend it to the multiple query. Yeah, we just do the same thing. If the algorithm, no, for the multiple query problem, here we use the G to control the HZ or the HX. So this lifting theorem only apply to the, basically, in principle, only apply to the problem that requires a single query verification, like this. So for the complicated problem, we need to reprogram multiple points, and this is that. For the multiple query verification or something, it's just sample multiple points, k points, and to this. Whenever the query index is equal to sum of them, it reprogram G. It queries H to get the output and reprogram G. Otherwise, it just use G. Here, I override G, so G will be reprogrammed 8 times at most. And every other things are the same. We can show that for any oracle G and H and any reprogramming point x1 to xk star and outcome Z, this inequality holds. Here we only make the k queries, and we can reprogram k points or control k points. So for the collision, we use this for k is equal to 2 and take the average of the oracles and some average Z such that x1 and summing every Z that is just a 2 input points such that hx1 and hx2 becomes the same. And the lifting theorem can be applied this. For the collision finding probability, lifting theorem make a t plus 1 square vector. And the remainder part is about B. And since B just query x1 and x2 to H, x1 and hx1 and hx2 are essentially random, and this two is the same. Yeah. And in general, we can think about the arbitrary relation between the input and output and some further string. And by applying the same arguments, we obtain this kind of lifting theorem. Here H make the T queries, but it is upper bounded by some factor times the advantage of another adversary that make only K queries. This is kind of the essence of lifting theorem, at least for the classical case. We could actually extend it to the interactive game setting. To do so, we just forward A's message and challenger's message to the others, and I will not check the details. So this is the classical lifting. Do you have any question about the classical lifting part? Otherwise, I just proceed to the quantum lifting. For the quantum lifting, I need to use some quantum, and we will consider the algorithm that access to the quantum oracle. Yeah, probably you see this kind of thing, which is the quantum oracle access to H. Actually, I will not use this. What I will use is only this, the projector. This is the projective projector that measure the register includes X or not. I will only use this, or a little more about the quantum. And we want to use the same simulator, but there are obvious problems. For example, A is quantum, so there is no J query. It is superposition of the input, and the obvious idea is just measure and use that Xi or Xj as the reprogramming point. It actually works, and I will show how to prove that kind of thing. Recorded in the classical setting, we use the reprogrammed oracle here. So it may be good to analyze the reprogrammed oracle algorithm. So we are thinking about the algorithm A that has a quantum access to G prime, which is the G, but reprogram X to HX. By the way, it is actually, I will explain the high level idea of the so-called measure and reprogram lemma, if you know. And if the algorithm may have access to G prime, then its behavior is basically represented by input, the unitary, query, unitary, and so on. This is the representation of A. We will use this. So we will analyze the algorithm A with respect to the quantum access to G prime, the reprogrammed oracle. And we will see the first query, the state after first query. But here we do some artificial thing. Instead of thinking about this, we add the identity here inside in the middle and write the identity as I minus this projection to X plus projection to X. This is obviously I. And we will decompose these two. Here, you can see that this part say that we measure the input register and we didn't see X. However, G prime is the G except for the reprogramming at X. So in this branch, OG prime must act as a OG. So this should be the same as this. By expanding this, we get the street term while we are analyzing the reprogram oracle algorithm. We have two terms with the oracle access to G. So we can kind of interpret this street term like this. The first term is just we do nothing and query G. And the second term is we measure the input register and observe X and the query G. The third term is we measure the input register and get X and query G prime. Yeah, we do the same thing, but for the green term and blue term, we just proceed the algorithm part. The other part, just preserve everything. U, G prime, U, G prime, U, G prime, or whatever. But for the red part, we do the previous analysis again. So what I mean is for the second query, we put the identity inside and write this one as I minus projection to x plus projection to x and decompose it to the I minus x and x. And here we can apply the same argument. This projection say that we are not calling x, so OG prime must be same as OG. So we have the three term. As you can see, we can do the same thing for the red term, and for green term and blue term, we just follow the algorithm. So repeating this decomposition for every query, we obtain 2t plus 1 term. The one term is this lead. Just everything's a lead and every queries are replaced by G prime and OG. And there are T green terms where the first term is just measure the first register and query G. Then later we do not anything and query G prime. The second term is we measure the second query and obtain X and query G and to proceed. We can understand that this thing as this. We just query G up to I minus 1's query. And at the i's query, we measure and see X and answer i's query using G. And then later queries are all answered by G prime. The blue term is very similar, but a difference is after measurement, we answer the query using G prime instead of G for the measurement query. So we have this. The final state with respect to the reprogrammed oracle G prime is decomposed into this. And we just compute the norm and apply the Cauchy-Schwarz. This is the 2t plus 1 term. And we separate every term. By dividing 2t plus 1 square, we get this. As you can see, this is the expectation of something. And it turns out that this leads to the simulation. But here, simulation is a little different. The simulator not just sample the query index, but sample the index B, which is just 0 or 1. Of course, we need to include the both. So this is a 2t plus 1 element group, a null set. And the query, it sample its own random oracle or own arbitrary oracle actually, and learn A in a following manner. If the sampled query, sampled thing is both, it just use the random, the oracle G, its own oracle G to answer everything to A. But in other case, for the first I minus 1 queries are answered using G, and for the i's query, it measures the input at obtain X, and for X, it queries to the H and then obtain HX. And the next query is answered by G or G prime depending on B. Then later queries are answered using G prime. B outputs whatever A outputs. That's a new quantum version of the simulation. And with some ambiguity. This term is bounded lower bound of this simulator. And this is the upper bound of, we observe this. So this is the upper bound of the algorithm's A success probability. So we obtain this for any oracle G and H and any input X and outcome Z. This inequality holds. And we do the same analysis as in the classical. We just summing everything over the oracle and summing every x and z such that x is equal to g and z is 0. We get this. And as you can see in the simulator, P always make the classical query to the oracle H because whenever it query to H, it measures the input. And this is a single query algorithm, so the success probability of this part is just 1 over y. So we have this asymptotic upper bound of the one-way is preimage finding of 0. And we can do this thing for arbitrary many queries, k, and we obtain the analogous to the classical setting, but just change thing is exponent. We change k to the 2k and t to the 2t. We know that we make the classical k queries to the oracle H. So this is the quantum lifting theorem for the function. I will not discuss the applications. Any question about quantum lifting theorem for function? No? I think I can finish a bit earlier because for computation I will not barely explain things. So this is about the function. What is the problem of applying this thing to the permutation? It's pretty simple. If we just think about the reprogramming of the permutation, this is not a permutation. Why? In diagram, we can see this. We are thinking about the point A, B, and yeah, A is supposed to be go to PA, but the reprogramming says that, okay, just forget about PA and A should go to B. There is two problem. There is no input to go to PA, so it should be not a permutation, and P inverse B should go to B, so there is a collision. Of course, there is a problem with inverse, but for this approach, it is not a big problem. And as you can see the thing in this diagram, we can easily find the resolution of this reprogramming. Instead of just reprogramming 1 point, we just reprogramming 2 points. It's pretty easy. So we just define a permutation reprogramming in this manner. When we reprogramming A to B, we also reprogramming P minus B to PA. And we also need to define the P inverse in a similar way. PA should go to P inverse B and B should go to A. Somehow, surprisingly, it just resolves everything. Perhaps a bit non-trivial thing is the decomposition we discussed, but it's not very complicated, I believe. Instead of just removing the input x, we need to remove two inputs, a and a prime, because we reprogram 2 points. So after doing this calculation, for this measurement stuff, P prime is effectively the same as P. So we just change it to P and we get the 5 term instead of a 3 term. And we do the same thing to this term. So we will eventually get a 40 plus 1 term and we can use the same interpretation. This thing is, we just don't do anything and query P instead of P prime. And here we measure the first query and obtain one of A or A prime and query P. For here, everything is similar, but we query P prime for the first query. And based on this, we can do the same thing as a function. Everything goes smoothly except for one thing. Because we need to choose this kind of point for every reprogramming point, there is a probability that collision exists, but it turns out that it is not a big problem. And we can show this thing. I think in the paper we put 8 here because we allow the superposition of inverse and forward query. But this is basically the ideal. It's a pretty simple. And in our paper, we discussed a few applications. And yeah, as you can see, it's all pretty nice. We are starting from a quantum adversary with many queries, but we eventually get a classical adversary with a few queries. So, and we already know that it is pretty safe. But the problem is this term. It's all huge. So, for example, if we are thinking about the sponge, Hhan sponge, the sponges that need to query the permutation phi multiple times. So our theorems for the sponge looks like this. If we are thinking about the problem with the k points, then because each query to the sponge require L query to the permutation, and since there are k points, we have an exponent of kl, which means the term is exceedingly large. This is from our lifting theorem, and this too is just because of this term. And this term is just a classical indifferentiability, because after applying the lifting theorem, we are in the classical situation, so we can apply the classical indifferentiability to argue the security. And this is just a random oracle analysis. And the results look like this. We can show that sponge is one way, even with the quantum query to the permutation, but the security is miserably bad. For the Hlan, the exponent is about q to the 4l. And for the collision, we can do the same thing. But I think when we write the paper, this is the first quantum security proof for the sponge. Now we have a little better one, much better one. And we also discuss about the multi-collision of the constant Laurent sponge or security of Davis-Meyer or the research problem for the permutation. And finally, I can discuss the obvious limitation in open problems. This loss is exceedingly bad, super large. But for example, even for the collision problem of a random oracle, this lifting theorem only gives a t to the 4 lower bound. But we know that the collision finding has a t to the cube lower bound. I think there may be a way to prove this one using lifting lemma, lifting theorem. So I believe this is one of the best open question at this stage. But we know that removing the dependency on k is impossible, or at least we need to have some term about k. The reason is the famous Yamakawa-Janke paper. They found that an explicit example that for the random oracle, some one-way problem is classically hard but quantumly easy. And for that problem, the number of verification requires linear number. I think their motivation is the lifting theorem they have. and there is some improvements. But for example, as you can see, we just randomly choose k points to reprogram. Probably we can choose them simultaneously and do something, which lead this kind of improvement. But it's about k factorial. But the problem is if we do this lifting, the resulting algorithm B is quantum, not the classical. So we need to analyze the quantum algorithm that make a small number of query. But based on this, these guys prove some interesting implication. But the limitation is here is still 2k. And everything's are about the search problem or the problem that allows the verification. Obvious question is what about the decision problem? It is more important questions, but uh, obvious ways you can apply the one-way to hiding lemma to extract some to make the problem to one way, but it give another loss on top of this, so it's not the best idea. There are some results, but I'm not sure I can call it
Sorry,
good.
Minky, for the one way to hiding, like to apply it, it will give only one more t, right? A factor of t on top of what you have. Like usually
Yes. Oh yeah, yeah,
so it should not be that much given what you already have.
yeah. Maybe that's right. Let me think. Yeah, probably that's a good point. But hmm.
Yeah, but
Okay, I think another problem is that one-way problem is I'm not sure we can find the verification for that one-way problem always.
yeah.
Yeah, so it may be hard to apply the lifting theorem.
Minki,
Yeah.
so a small question. So the indifferentiability result you said, so isn't that like, don't you treat it as a decision problem? Indifferentiability?
Oh, you mean this one?
Yes.
No, here by the lifting we just change the problem to the classical sponge access. Then we just
Yes.
change that classical sponge to the random worker using the indifferentiability.
Oh,
So we just
so
change.
what you are solving is one-wayness, like pre-image resistance. Yeah.
Oh yeah, I mean we just use the indifferentiability to change the problem about sponge to the problem of random worker.
Okay. So
Yeah, thank you. Yeah. So, is there any other question? May I finish this slide first? So there is, as far as I know, there is the one lifting theorem for the pseudo-random generator that is generated by the random oracle, but I'm not sure it is the right way or it's the good way. They conjecture that they can extend it to the random pseudo-random function, but their loss is already huge and I don't know. And for this direction, we have some very indirect evidences. For example, for the worst case query complexity, we already know that the random randomized query complexity and quantum complexity is related by force exponent, but it's about the worst case. And for the average case, I don't know. I feel that we need something like Aronson-Bennett's conjecture, but I'm not fully sure. And recently also Yamada showed that for the indifferentiability, we cannot hope because some probably Davis Meyer is some I don't really remember the technical term. Davis Meyer is classically somewhat indifferentiable, but quantumly not. So I think This is a good question, which I don't know how to. So that's it. Thank you for listening. Any further question?
Thank you for the talk. And I do have one question. So from your lifting theorem, I guess you always assume there is a one single oracle. So does this lifting theorem can support like the adversary interact with the many oracles? Like for example, multi-user security or a construction using different independent permutations?
I think we can apply this for Oracle one by one manner, as
And
long as
then
they are independent.
will the security loss will be just like linear, just additional, or
No,
the
no
loss will be multiple?
multiplicative. We need to
That's
multiply this vector.
okay, that's bad.
Yeah, that's bad.
And so also someone who are not familiar with quantum stuffs, can you give a like brief comparison between the lifting theorems and the compression oracles? What if I prove something using the lifting theorem and using compression oracles? What is the difference?
I think, okay, in my opinion, compressed oracle is the quantum version of the lazy sampling. So you will have a kind of database, but the problem is the database is in superposition, and whenever you query, the database is changes a bit strange way. I mean, it changes. Almost all portions are changed as you expected, but some portions are behave very differently. So when you want to use a compressed oracle, you need to analyze the database query by query manner. So you need to study quantum. But for this one, although it has a bad bound, it's kind of upgrade. If you ignore this kind of proof, you can just use this one, quantum to classical. Yeah, that's it, I think.
Okay, thank you. Is there any question from other people? If
Yeah,
not,
I have one more. I saw like you have one application on indifferentiability. What about indistinguishability? Like, did you try the Feistel problem with your lifting result? Like trying to prove the Feistel indistinguishability with the lifting.
No, I don't think so.
And what do you think about the difficulty there, or do you think it is approachable?
Okay, I think this kind of lifting theorem for search problems are heavily based on that the outcome of algorithm or verifications are done by classical queries. And that kind of verification is simulated basically.
Mm-hmm.
But for the decisional problem, it is unclear what to simulate. So because of that, the many papers just directly simulate the algorithm only using the classical queries. And of course, it should be very complicated. Just naive simulation already require exponential flow.
Like,
And
so,
this,
uh,
yeah.
so basically what I was thinking is whether combining the lifting idea, especially the way you were dividing the input state into one particular target input and the rest of the state. Like, if you can you do this like this measure and reprogram idea over the compressed oracle itself? Because then like there might be a way to rewrite the indistinguishability problem where you have like a very nice search problem, say some kind of collision problem,
Mm.
which is what we usually do in the classical setting as well, right? We have these bad events, which is basically there is a collision on the some intermediate value.
Yeah, that makes sense. I never thought about it. Yeah, I never tried to combine the compressor operator at this. Yeah, that might be a interesting question. Yeah, I will say I don't know. It's a good direction.
Also, you
Minki,
use,
sorry.
sorry, you first.
Yeah, sorry, Minki. Sorry for the sounds because I'm on a bus. But I wanted to ask whether you read this new paper of the compressed permutation oracle, and whether you try to maybe improve the result with the lifting theorem or try to compare how that work. Maybe you looked at that.
You mean the... Actually, there are too many compressed permutation oracle paper recently. Probably
Sorry.
you are talking about the Joseph paper
Yes. Yes.
with the most of 12 in the
Yes.
exponent.
Yeah.
Yeah, I think that paper is good, but the problem is we don't know how to remove the exponent. And another problem is there is a rumor that somebody get a tight compressed permutation oracle.
Oh. Okay.
I'm not sure. Yeah, they actually get a collision, go beyond the collision bound or something, but probably it is very tight. It is not out, so I just didn't do anything
Sure.
about the compressed permutation
Sure.
oracle stuff.
Sure. Okay. Thank you.
Okay, so let me back to my question. So you use the indifferentiability to turn your sponge construction to random oracle, but
Mhm.
you know there are like few limitation on applying indifferentiability. Say like if the game is multi-stage, then it doesn't work. So I'm not sure whether like your setting is applicable by indifferentiability or not. So did you ever thought about it?
No, of course not. We are basically study the one round problem like one-way or collision finding. So I think in this setting there is no problem. But yeah, maybe that's right.
There might be a problem, right?
Yeah, there might be a problem.
It's very like dedicated definition, so
Yeah,
it, it might cause problem.
I see. Thank you.
Anyway, maybe we can stop the recording and then discuss offline.
I see.
Yes, so we will maintain the discussion thread so we can keep discussing for this kind of very interesting problems and glad to see your enthusiasms. Just like so I have one announcement, so before I forget announcing this and somebody leave. Uh so we plan to have a next talk by April 30th, given by Viet Tong Huang. So we plan to do that. So everything is not fixed, but we will announce very soon within a few days, hopefully with a concrete plan. So please keep your eyes on our website and thank you for attend